Hello everyone, I'm Ramanpreet Singh Pahava from I-Score A-Star, and today I'll be presenting our work titled Machine Learning Based Methodologies for 3D X-ray Measurement, Characterization, and Optimization for Buried Structures in Advanced IC Packages. Long title, but in short, what we want to do is what's shown in the figure here. Given certain structures that may be present in 3D data, we want to be able to automatically identify where they are, what they are, do their segmentation, basically figure out their dimensions in 3D, and then be able to infer certain anomalies that may be present in them in future. So let's get started. In this talk, I will first motivate the problem statement, why what we are doing is important. Then I'll discuss the fabrication of the test vehicles. Over here, we use TSVs and HPMs. I will discuss the protocols involved with data collection using 3D XRM tool. And then I'll dig deep into the technical aspects of automated 3D metrology, which involves 4 steps: 3D annotation, 3D object detection, 3D segmentation, and 3D metrology. And once I'm done with the discussion on the technical aspects, I will showcase our results on the data that we've collected, and then I'll conclude this talk by talking about what there is in future to improve these results. Okay. So advanced package interconnects have taken giant leaps in the last 30 to 40 years. We have gone from interconnects of sizes from 150 micrometers to less than 30 micrometers now. And in future, we might even see interconnects that will be 20 micrometers or even 5 micrometers. On the flip side, we have gone from 50 IO per millimeter square in 1980s to now more than 1,000 or even 20,000 IO per millimeter square in future. So there is a big improvement in terms of pushing the size as small as possible and adding more and more information in a given area. However, it also comes with certain drawbacks. We have gone from very high yields to now in future even yields that might be too low for mass production. What this will involve is basically manually checking the quality of these interconnects, and currently the way it's done a lot of areas is you manually look at them via 3D XRM tools, or you perform cross-sectioning to look at why they are not working or what is the problem there. And what we want to do is essentially add some AI-based technology on top to make this more automated, so you're able to do it quickly and fast as possible. So in essence, doing this currently is very time-consuming. It's prone to human errors. So there is a real need for automated 3D metrology. So as in other areas, we are moving towards AI-based automation. This automation will involve several integral steps that we need to be very careful about. This is fabrication, how you fabricate the data, the know-how of TSVs and HPMs, how the data collection is done, to understand how the tools are collecting the data, what are their pros and cons. Then once the data is collected, we need to annotate the data to train our models, to understand where these structures are, what these structures are, and so on. And then we need to perform our data analysis to extract the relevant information out from there for the process engineers. So in short, what we want to do for this work is, given these 3D regions or 2D slices, we want to be able to segment out the structures and then be able to perform automated 3D metrology, which is measuring their dimensions, the width, height, depth, which gives us important information about the structures. So let's get started with fabrication. Now, 2.5D systems in package consists of multiple device and package assembled on TSV interposer. In this work, we are essentially going to be focusing on 2 packaging interconnects through silicon vias, TSVs for short, and solder-based bumps. Essentially, we'll be looking at memory and logic bumps in this talk. And it's very important that we can integrate some machine learning, deep learning to measure these physical attributes and detect the defects of these packaging interconnects, because it will be beneficial for the development and manufacturing processes of this 2.5D systems in package. Okay, so for TSV fabrication process, we first start with silicon substrate. Once we have the silicon substrate, we do photoresist patterning, followed by DRE etching. And after that, we do a chemical clean and photoresist stripping, as you can see in the figure, followed by linear deposition, and at the very end we'll do copper seed deposition, and super conformal plating to create void-free TSVs. So essentially, this is how we will create and fabricate our TSVs. And after that, we'll be using a 3D XRM tool to measure the TSV width, depth, and height. In a similar protocol, we also fabricate our memory bumps and copper bumps using copper pillar die fabrication. And the step that we follow for this is basically we take in our copper pillar bumping, and after that we perform temporary bonding to carrier. This is further followed by wafer thinning, and then we do copper pad processing. After that, we'll do wafer debonding and cleaning, and which is followed by wafer level underfill lamination. And after that, we'll basically dice it to die and then perform our assembly on the logic wafer to get our logic bumps and memory bumps. And similar to TSVs, we will use 3D XRM tool to measure their width, height, and depth for testing. So once we have collected this data, we have fabricated the data, we have performed our measurement, the next step would be to maybe visualize the data or to analyze the data. And for that, we use our own 3D data analytics software tool for both the visualization, processing, as well as certain analysis. Essentially, what it does is it takes in the 2D virtual slices that is obtained and overlays them onto a 3D volume. So that way we can look at the data in both 2D and 3D. It's also used to identify and annotate TSV structures and interconnects. Another advantage of this tool is that we are able to label both positive and negative examples, which helps our training method to understand what is a TSV and what is not a TSV. Moreover, it can also be used for visualization of results at the end to display characterizations such as bond line thickness and defects such as voids and pad misalignment that we might be working in the future. Okay, now let's get more into the detail of the AI-based 3D metrology that we are looking at in this paper. As I mentioned before, it involves 4 major steps: 3D annotation, 3D object detection, 3D segmentation, and 3D metrology. So once we have fabricated this data and measured this data, the next step is figuring out how much data we want to annotate or collect, right? For object detection, which is essentially finding some 3D boundaries around these structures. For TSVs, we have about 300 structures that we labeled. For memory bumps, about 2000, and for logic bumps, about 1200 structures. And you will see in the coming slides that how object detection is done and why we can label so much data for object detection. In segmentation, you will see that labeling this data is extremely hard and time consuming, hence significantly less amount of data is labeled for this work. For TSVs, we label 13 structures. For memory and logic bumps, we label 8 structures each. So as I mentioned, now over here we are showing our labeling for 3D object detection for TSVs, for memory, and for logic bumps over here, right? So you can see that what we do is, given the 3D sample in our software tool, we draw 3D bounding boxes around these structures, as you can see over here. And we can do that for TSVs as well as memory as well as the logic bumps. So essentially for each of these structures, we divide them into 3 classes: the TSVs, memory, and logic die, and we try to label very tight bounding boxes as possible. What this essentially involves is, if you think about it, drawing a rectangle and then extending it in 3D to make it a 3D bounding box. So this part is relatively very simple and fast. All you have to do is figure out the boundaries, draw these cuboids, and you're done. And hence we are able to label so much data for training. Meanwhile, for segmentation, what we need to label is essentially voxels. Now, what is a voxel? Voxel is actually a 3D pixel. So the images that we take from our phone cameras or DSLR cameras essentially is a 2D planar data, which consists of these squares that contain some intensity information, right? So now think of extending that in 3D, so you get like a volumetric pixel, right? So each of these 3D regions will basically contain a 3D volume inside, and that's a voxel. So for each of these 3D bounding box regions that we had isolated, we need to identify what is a background and what is a foreground, and thus there are two classes for each of these three different structures. So we will basically label for each of these areas that this is foreground and this is background, and doing that for each slice for in 2D and 3D is very time consuming. It requires very careful annotation, especially at the edges. Hence, this is very slow. So we label about 13 TSVs and 8 memory and logic bumps for this work. And you can see that the final labeling looks like this, which is very detailed and thus requires a lot of effort to do. So once we have labeled the data, the next step is 3D object detection, which is figuring out where these structures are in the sample. And there can be hundreds to 500s of these structures inside the same sample. So we need to be able to detect all of them without any skips, all of them very accurately with tight 3D bounding boxes. And there are two ways to do that. One is crudely to do this in 3D directly. Try to, given a 3D sample, we train a model such that the output is essentially a series of these 3D bounding boxes that tell us the starting point for each of these areas, as well as to tell us the width, height, and depth tightly for these structures. Currently, this is not computationally possible. Each of these scans is 1000 by 1000 by 1000. This results in 1 billion voxels. So imagine having to do this object detection for each 1 billion voxels. It's just currently not very feasible. One way to do that would be you try to basically divide the data into smaller regions, or you can downsample the data, but that leads to loss in accuracy sometimes. The other way to go about solving this issue is by detecting these structures in 2D for each of the 2D virtual slices, and then combining this information together to find a 3D bounding box. The advantage of this is that it has very good performance in terms of accuracy. It's computationally very fast and light on the memory. Hence, this is the approach we adopt for this work. So we have, as I mentioned, we call this a slice and fuse approach. What we do is, given our 3D input volume, which is about, as I mentioned, about 1 billion voxels, we will slice them into 2D slices. And for each of these 2D slices, we use a single shot detector to identify tight 2D bounding boxes around this region. Once we have collected these 2D bounding boxes around the region for each of these different slices, we combine them together into fused 3D predictions to get tight 3D bounding boxes. This also involves some novelty, where it can happen that you somehow miss some bounding box detections in some slices inside the array. So we basically try to make it more robust, but even if we skip a few detections, we are still able to recover that in the final 3D bounding box estimation. For this work, we trained 3 independent models, one for TSV, one for HP, one for logic die, and one for memory die. And it took us 16 hours to train each model on a very high-end GPU. So even in 2D, it takes 16 hours to train. So imagine how it would be in 3D. So once we have identified and isolated these structures in 3D, the next step would be to perform 3D segmentation. For each of those isolated structures, we need to identify what's a foreground, what's a background. And since this isolated structure is much smaller in size, so our patch size is about 20 by 128 by 128. This is about 300,000 voxels, which is significantly smaller than the resolution, 1 billion voxel resolution we started with. We use a 3D anisotropic convolution neural network for segmentation. Essentially, this network involves 10 residual blocks that you see over here in blue. These blocks come with anisotropic convolution, some dilated convolutions, and multi-scale predictions. Essentially, it tries to learn local and low-level features as well as some high-level features. The local and low-level features are learned in the shallow layers, and they refer to like the edges that may be present in the scene. While in the deeper layers, we are trying to learn some more high-level features, which would be the patterns that are there in the images, or in the data, or the shape of the structure itself. And because this technique is borrowed from medical imaging, essentially the three planes that we talk about there are coronal, sagittal, and axial views. So we train an anisotropic CNN model for each of these three views individually. So in a way, we can slice using the axial plane, or we can slice using the sagittal plane, or we can slice using the coronal plane. So that way we are basically getting three different segmentations for each of these isolated structures. And after that, we combine the information from these three different segmentations together in a smart way to get a more accurate segmentation in 3D. So once we have done the segmentation in 3D, the next step would be to measure the dimensions of these objects that may be present there. So again, we take a slice and fuse approach. We basically get this 3D segmentation. We divide them into 2D slices. We perform our metrology, 2D metrology on each of these 2D slices separately. So we sort of estimate a rectangle around each slice, which is represented by 4 parameters. X, Y over here would refer to where the object is starting, and W and H refers to the width and the height of what is the dimension of that region that we are looking for. And we do that for each of these slices. So essentially, as you go from structure from slices in the structure, you go from very small boundaries to the biggest boundary somewhere in the middle, and then you again get to smaller rectangles, as you can see over here. We combine this information together to get a 3D cuboid for the tightest dimension estimation possible. So for this, the format would be XYZ WHD, an extension of 2D rectangle. So essentially this would be your starting point, and width, height, and depth would be represented by WH and D, which are basically the dimensions of this. So you can think of height as like a bond line thickness, where we measure the height for each of these structures. Okay, so now that we have discussed the technique that we use for our work, now we'll show some experimental results. But before we get started, let me just dig a bit deep into how we train our models and how we split our data. So we use a standard train val test split approach that we use in machine learning. Essentially, the data is divided into 3 subsets. Train is about 85% of the data, validation would be about 5 to 10%, and testing would also be 5 to 10% of the data. The model contains sort of 2 different types of parameters. So there's something called model weights. So these model weights are tuned based on the training data over here. There's some hyperparameters such as the learning rate, the batch size, and so on, that will be trained based on the validation data over here. And then we have the test data, which is the data that is used to evaluate the model accuracy. Our model will never ever see test data for training their weights or the hyperparameters. So in a sense, we get this very unbiased view of what the model's performance is, because this data was never ever seen by the model. So for our work, we divided the data into train val test. For this SSD detector, it does not use a validation split, so we just divided the data into train and test. And for segmentation, we did about 85 to 5 to 10 split. So in a sense, for 13 TSVs, we had 7 TSVs for training, 2 for validation, and 4 for testing. And for logic and memory die, out of the 8 labeled structures, we had 5 for training, 1 for validation, and 2 for testing each. A couple of other concepts we want to discuss are, first is intersection over union. So what does an IOU mean? As the name suggests, it's intersection divided by union. So given a ground truth 2D bounding box that you can see in the rectangle over here, and let's say our prediction is this blue box, the intersection is given by this common region inside, and union would be the union of these 2 bounding boxes. So if what we want to get is a very high intersection over union as possible, this number will vary between 0 and 1. Let's say our prediction was actually something like this. Now the intersection of these 2 will be 0. So our IOU will be 0, which is really, really bad. So what we want is like a very tight bounding box, something like what you see over here, where intersection and union would be almost similar values. The reason why this works really well is because it also avoids issues such as, what if I just draw a very big bounding box around this region, right? And I can say that, look, this bounding box contains the ground truth inside, but it's not really compact. So the intersection over here would be this smaller ground truth bounding box, while the union will be really, really big, and hence our IOU will be small. So this is a very good metric to actually evaluate the results and train our models as well. The other concept that we use for training is dice coefficient. Now, dice coefficient is essentially 2 times the intersection divided by the sum of those two regions. So instead of union, we use a sum. So you can see that conceptually it's very similar to the IOU metric. It's just that dice score is widely used for 3D segmentation training, while IOU is commonly used for object detection. In general, the IOU metric tends to penalize single instances of bad classification more than the dice score quantitatively, even when they both agree that this one instance is bad. So essentially that's the small difference in the two. Now, the results for 3D object detection are shown over here for both training and testing. So for training, we can see that we get about 98 to 99% accuracy for average precision for any IOU above 0.5. For testing, in contrast, you can see that we are also get about similar results for logic and memory bumps. For TSVs, they're somewhat lower. And the reason is that TSVs sometimes, especially at edges, gets a bit blurry. So it's difficult to get a very tight fitting bounding box that agrees with the ground truth sometimes. We also report our 3D IOU results. If we had reported our 3D IOU with anything above 0.5 as a success, then you can see that roughly speaking, everything will be accepted as success and will get like 111 for average precision. Hence, we may show our raw results, because it's also important to not just have a good and enough intersection. You want this number to be as high as possible. Thus, there is some scope for improvement in 3D IOU in future, and we plan to continue working on it to improve the results in future. Now we show our results for 3D segmentation. So the hyperparameters we use for our model training are shown on the left. We use the dice loss that we explained before. Our optimizer was Adam, and we had the following learning rate, batch size, and we use 100,000 iterations for our model training. On the right side, you see the 3D dice scores, and you can there's some similar observations compared to 3D object detection, that our dice scores on logic and memory die are higher than what we see in TSVs. There's definitely some scope for improvement here, because if you look at some state-of-the-art techniques in medical imaging domain, you can get up to 95 to 99% accuracy. Meanwhile, over here, we are only touching maybe 91 to 92 for TSVs. So there is some scope for improvement. The data over here sometimes gets challenging because it's very difficult to know where the edges of the TSVs are. And moreover, we have very little data for training right now. While in medical imaging domain, you have access to hundreds to thousands of training data. So we definitely plan to improve the results, hopefully, in future. Now let's look at the results in a more qualitative way in some visual results. On the left side, you see the 3D object detection results for memory bumps. The logic and your TSVs also look very similar. So we get very tight 3D bounding boxes. There are absolutely no skips. You're able to detect all of the structures in one shot. And for 3D segmentation, the left side you see a virtual slice, a 2D virtual slice, and on the right side you see the 3D ground truth segmentation. In the middle, the second column shows our 2D segmentation projected on it, and in the third column we see our results. You can see that clearly we are also able to do a really good job in terms of 3D segmentation, except that our boundaries are not as sharp as the hand annotation ones. And this is the part that we do plan to improve in future. So now we report our results for 3D metrology. So essentially we measured the ground truth dimensions of these structures, and then we, without manually measuring anything, we went from given some data, run our object detector, then run our segmentation, and then perform our 3D metrology and get the dimensions. So we are comparing those two directly over here. And height over here, roughly, I mean, this actually represents the bond line thickness. On an average, we get about 2.1 micrometer errors, which corresponds to about 3 voxels. We definitely want to reduce it further down to less than 1 to 2 micrometers. Once we have perhaps sharper edges, this would give us better results in future. So in conclusion, we presented our approach on automated 3D metrology for different test structures such as your TSVs, memory die, and logic die. We demonstrated the fabrication steps as well as how we measure the data in 3D. After that, we discussed our 3D deep learning approach for object detection, segmentation, and metrology. The results are very encouraging, but there's definitely scope for improvement. In future, we want to look at multi-class segmentation where we're able to separate out copper pillar, copper pad, bumps, perform 3D metrology, look at different defects such as voids or pad misalignment. So there's a lot of good work that we can do in future with these test structures. Thank you for your time. If you have any questions, feedback, or queries, feel free to email me over here. I look forward to hearing from you.